It's a national capability that provides a unique access to space that America has not had in 40 years.
A large launch vehicle like this really opens the door to destinations beyond. It's not limited by destination. It's only limited really by imagination.
What we're focused on here at this center is the propulsion system. And that consists of 2 solid rocket boosters and a core with some tanks that feed some liquid rocket engines in the middle. And then the astronauts sit on the top in the Orion spacecraft.
One of the things we recognized for SLS is we had to be affordable. So we had to do things differently, more efficiently, and smarter.
We're all conscious about saving money, doing it more affordable than we have in the past. But at the same time, we can't sacrifice reliability or safety.
The system uses a significant amount of heritage hardware, which is things that we've evolved from the Space Shuttle program.
The Space Shuttle had 2 kind of candle-looking things, which are the solid rockets. Those are kept, and those are used on SLS.
We've added a segment to the 4-segment solid rocket boosters that we had on shuttle. That gives it more power, more thrust, and it helps this larger rocket get off the ground. What those boosters are for is just to get you going. They burn for a couple of minutes and then they fall to the ground. Then your liquid engines, you're up high enough, your liquid engines can carry your vehicle to as high as you want to go, and if you have additional stages, like we're going to have one, then you can go further out into space.
Right now the inventory that we've got consists of 14 engines that have flown on shuttle. We've got 1 engine that was assembled and still needs green run testing or certification testing. We looked at all the spares. As we collected the spares, we determined that we could assemble a 16th engine. So we'll have 16 engines that we'll be able to use for flight.
We are making tremendous progress. We've got all of our prime contractors on board. We're testing engines, we're testing solid rocket boosters, our avionics systems.
J2X has recently set a record at Stennis. When we were testing, it was the first liquid oxygen engine to get to a full duration test in 4 tests.
We were developing this booster under the Ares program, and we're moving that into the SLS vehicle. The motor itself has been through 3 development firings, which are full-scale motors tested out in Utah, and we've gotten a lot of good data, engineering data from those tests.
This is an adapter that goes between the bottom of the Orion capsule and the top of the Space Launch System rocket that we're developing here at Marshall. It's been specifically designed to give strength to the adapter so that it can take the loads in flight and still be lightweight. This shape started out as a series of flat panels. The isogrid pattern was machined into the surfaces. Then they were formed, it was called in a process called bump forming, to make them into the shape that we need here. And we weld 3 of these segments together to form the cone that you see behind me.
We just delivered the first crew module to the O&C building at KSC. We started a lot of the parts onto the outside of the CM, and we've actually put it in what we call the bird cage, so we can locate all those parts, within, thousandths of an inch to make sure that everything is going together okay.
Putting, wiring inside of it, putting tubes for the, for the propulsion system, putting valves and pumps, and so all of that happens in stages right there in the O&C building.
We have on contract with USA, United Space Alliance, to build our harnesses. They're set up shop in the O&C, and so their little shop delivers to the big shop.
Thermal protection is very difficult in re-entry vehicles to test and to model. I mean, really, you have to fly it to really understand what's going to happen. We're building ceramic thermal insulation tiles for the back shell of the capsule. We're building thermal barriers for the capsule, and we're building multi-layer insulation for that capsule.
I'm the heat shield design lead. So we're designing and building the heat shield for the future Orion missions.
The heat shield right now is in our big 20 by 20 router. It's a 5-axis router, and right now it's machining the interior bowl, if you will, of the heat shield.
To cut out that heat shield on the router could take weeks of machine time running multiple shifts.
It's the biggest heat shield ever constructed.
The other component is the heat shield skeleton, so that's the piece of the titanium substructure, the backbone that makes up the carrier structure itself.
Another unique thing is all the hand drilling that we're doing. So it's not automated by a router in this case, and it all has to be hand drilled by technicians on the inside.
200 plus titanium parts, all match drilled together.
So we have a tool that puts all the pieces in the right spot, and then we drill and high lock them all together.
MCC is transforming from supporting Space Shuttle and Space Station to a platform that will support Space Station and MPCB or Orion.
In order to adapt for the future, we need to go to a more modern system.
KSC will operate the vehicle all the way up until launch. We'll operate the vehicle until splashdown, and the recovery forces come in and take over after that.
Fire Room 1 is the launch control room we're going to use for Orion SLS for EM1 missions. We've been working with the Orion program to get the spacecraft data so we can process it with our software in the fire room, and we will be flight following that mission out of Fire Room 1. We refitted the room, we redid it, putting the sound suppression carpeting on the walls, making it kind of a more comfortable place to work. So we're aiming for about 50 people in Fire Room 1 for an EM1 mission. We are actually using Fire Room 1 right now to test Pad B subsystems.
This pad is going to be almost like a complete new pad because we will have refurbished each and every system that it's inside the pad. We're going to have the vehicle launch from the mobile launcher, and not only launch from the mobile launcher, but have a tower that will have all the services attached to the vehicle. The tower is going to be on the mobile launcher. The vehicle will be assembled at the VAB.
It's a return to a concept that we knew that worked very well during the Apollo years, when the mobile launch platform had a tower on it. We knew that the VAB was designed to accommodate a launch tower on a mobile launch platform. We have to make sure that the VAB can remain adaptable and accommodate different vehicle architectures. And now we have a clean VAB shell, per se, the infrastructure, so that we can accommodate the new hardware, the new vehicle access with new platforms. And that is the first phase of what we're doing now.
And once the vehicle is ready with all the connections, the only thing we got to do is move the vehicle to the pad, do the connections to the mobile launcher. And once we do those connections, we're ready to launch.
There was a time where I had to explain what a crawler was. If you didn't work out here at the Space Center, or if you weren't in the Central Florida area, a lot of people just, somehow the vehicle got out to the pad. We knew what to expect from a load perspective with the new vehicle, the larger rocket, and things along those lines. And that goes from the crawler lifted load, the hydraulics, also to the crawler way. We're going to have to increase the load lifting capability for the crawler way itself with the rock. What we've essentially done is keep all the same hydraulic components, but just increase the size, the diameter of the hydraulic cylinders. Last November, we actually took a ride out with the completed crawler 2 out to the pad and tested out the systems and a couple punchless items, but everything worked great. The control system had been upgraded. The driver's cabs consoles had all been replaced. The brakes had all been replaced. Nearly every subsystem had some kind of work done to it. The traction support elements, each of the 4 corners has 22 rollers that are about the size of a car, to be honest with you, and we're changing out all of those, enlarging those as well.
What I love doing is reminding the outside world, whether it's within our government or especially the media, that has a perception that we're in a lull, there's nothing going on, that the space program's shutting down, to kind of dispel that rumor and say, no, this is the far opposite for us. We are utilizing this inter-program time frame to make all the modifications and all the infrastructure changes that it will help bring that agency vision into reality.
Many of us feel the country wants to go forward, and NASA has a big following, and every time I talk to people, they're excited about NASA.
Enabling people to go beyond where they have ever gone before and look and discover things that they didn't even know existed it's just a real honor.
It's been a pleasure to be involved with this project, and I can't say enough for the team that's put this together.
I'm privileged to work this program. I think most people who are working it today feel the same way.
I can't believe they pay me for this job. It's just wonderful. It's great.
This is probably the most exciting point in a program from the standpoint of activating the factory. The stage of the program that we're dealing with is called confidence hardware, and that's when we take flight form hardware, run it through all the tooling, use that for subsequent testing and fit-ups. All of the tooling that is going in is upsized to scale for the SLS program. Some of the vertical tooling is in a building that is probably 15 stories tall. The largest section of the rocket is the fuel tank, the hydrogen tank. You have to stack that with the other sections of the rocket, inner tank, the engine section, the forward skirt. Put all that together, and you've got a very large rocket. We're looking at completing the first flight vehicle at MAF in May of 2016, and we're on track for that.
SLM is selective laser melting. It's a method of turning powdered metal, finely grained powdered metal, into solid parts. The design is done straight from 3D CAD models, which is standard in the industry. You can use any kind of commercial software, and the machine takes that and cuts that into a bunch of slices and builds them slice by slice. What we have to do in order to trust the material is we have to do a lot of testing on the ground. Back in 2011, we built a duct using this process for the J2X, and we hot fired it. And what we saw was basically no deterioration of the material. We built the one part for 35 cents on the dollar. More complex parts, we think the cost savings approaches an order of magnitude. If this technology proves out like we think it will, the schedule savings and the cost savings is almost beyond imagination.
The work that we're doing here is to support the Orion test flight, which is EFT-1. The hardware that we're manufacturing here in this shop is the adapter for the Delta IV launch engine to the Orion test article. To complete the welded structure, you have 3 vertical or longitudinal welds that join the barrel panels into a cone. It moves from the vertical weld tool to the robotic weld tool for the circumferential welds. The circumferential welds are the welds that join the welded cone structure to the forward and aft ring flanges, and that pretty much provides your primary structure.
We within NASA are passionate about STEM.
SLS was at Tennessee Tech for Engineering Week. We sat on a panel and we did video talks with several different elementary, middle, and high school students.
Their Engineering Week, they have shared with us, usually draws about 70 people. And on a Friday night, one of our programs drew more than 400. The more that we can get people involved in those creative ways, the more successful we're going to be.
The outreach for inspiring the future is such an important goal of NASA's.
So we have to foster that inspiration and that dedication to learning that's necessary in order to keep NASA's dreams alive.
There's a lot of work going on the VAB getting ready for SLS and Orion coming in 17. In the VAB, we built a full-scale mock-up. The main thing we're looking for is the handling and access. What we're looking at is we're looking at getting some of the ogive panels from the GTA, which is the ground test article. They work great to do the practicing just like we used to see them in the last. We are working pretty heavy on the EFT1 part, and we're talking we're only 18 months away. The whole program, it's NASA successful. It's not just ground systems or Orion or SLS. So even though they're going off of Delta IV, having this flight successful does help SLS and GSDO. It's going to give us a lot of experience.
We did a one-year design on the entire crawlerway from the VAB to Pad A and from the VAB to Pad B. Over the years, the top-level rock has been refurbed multiple times. The actual foundation, the lime rock, which is what we're doing now, hasn't been refurbished since it was installed. We are reinstalling lime rock and bringing it back to print, and then we'll install some fresh river rock on top and then hopefully be good for another 50 years. Currently, the contract is about 20% complete. We're looking for a total completion date in mid-2014. The crawler transporter, as it finishes its upgrades, it will exercise or stretch and go up and down the crawlerway.
We have almost 47 different projects that touch almost every system on the crawler. The driver's cabs, the brakes, the generators. We're increasing the generator capacity so we're able to provide more power to the mobile launcher, to the vehicle, to the spacecraft. Within the next 2 weeks, we're going to be able to take the belts off the crawler, remove the old assemblies, and start assembling the new components in place, followed by the gel cylinders, the hydraulic cylinders. What the gel cylinders do when you're carrying a load, they automatically keep the crawler completely stabilized so the vehicle does not see any movement, especially when you're going up the ramp. After we complete the modifications, we'll be able to carry over 18 million pounds.
18 months from launch is not very far away, really, in the grand scheme of things. You think about trying to get all the systems on board. The guys are going great guns at putting all the secondary structure in, which absolutely has to be done right before they start putting the systems in. But you think about still all the wiring that needs to be done and all the plumbing that needs to be done and welded. Back in November, we had an issue. We took the pressure vessel to proof. We had a crack generated in the primary structure. So it was sort of all hands on deck, if you will, to go figure out what happened and why and how to fix it. And so we went in and just basically the guys created some fittings to offload the cracked part of the structure, and then the technicians at the ONC went in and cut the cracks out, and they're in the process of putting that all together now. So it'll be retested in April. For the next few weeks, we'll take a little bit of a back seat to getting the crew module through its big structural test. Then the structures guys will put focused attention onto the service module, getting it finished and built up, and then it goes through a structural test as well.
CPAS stands for the Capsule Parachute Assembly System. We are doing the development of the parachute system for Orion. The military have developed a technique called low velocity airdrops, and they set up the conditions for which then to start the sequence of the Orion parachute system. And so we work very hard to reduce the risk as much as we can, to understand as much as we can in order for when we do fly this crew, it's going to be a safe vehicle. So over the next 6 months, very happy that we will be delivering our parachutes to the Cape, to the ONC building to be installed in the EFT1 vehicle.
The NBL, we're kind of working on everything post-splashdown. We're working with the folks out of KSC and out of Patrick Air Force Base, and with Navy divers out of San Diego, putting together training material on how to actually go recover EFT1 out in the ocean. We're using Navy amphibious assault ships, and what they do is they can ballast down and lower the back end of the ship into the water, and we can hook the capsule up and just tow it into that well deck and set it down in a cradle. There's about 17 folks when we get a dive crew available. So what we'll do with them is we'll put 2 sets of 3 in small Zodiacs, and they'll do all the hands-on work on the vehicle. The cradle that we plan on using for recovery, it'll be finished within the next 30 days. We're delivering it out to Langley. And then in August, put that equipment in a well-decked ship and actually practice a recovery.
I think there was always a hope that I would be working on a vehicle that would carry humans farther outside of low Earth orbit, getting back into the roots of what NASA was built on, which is exploration.
What could be more exciting than building the next great outreach for the U.S. government and for mankind, actually?
You have to let people know that we're still here. Oh yes, shuttle did retire, but we are still making progress and we are still moving forward.
NASA's nowhere near slowing down. We're preparing for the future.
It's a great time for us to have such a tangible artifact of the work and the hours we put in. So yeah, we're really looking forward to EFT1. It's going to be good.
Very rarely do you get the opportunity to kind of literally from the ground up put together a factory whose sole purpose is to go make history and do exciting things for not just NASA, but for America and for the whole world.
We're in the process of getting the factory ready for SLS production. And in that process, there's a series of new tools that we've been installing in the factory.
Now we have not just put in new tooling, there's some legacy tooling that we're using. Most of the external tank buildings are being reused. We have a lot of construction going on for those, getting ready for a rocket that's same diameter but a little bit longer.
Not only are we using the legacy knowledge, the lessons learned, we're also incorporating new technologies.
The tool today is in the vertical friction stir welding center, and its job is to produce the cylinders that make up the parts of the tank that will be stacked.
And that is going to be the tool that joins every panel on every barrel for the rocket.
This device will actually do the weld in a single pass and then also do inspection. So these are the large barrel sections of the core stage that will be the foundation or the beginning rocket that will actually take our crews beyond the moon and really propel us into space.
Here at Marshall, we've designed the interface hardware in between the Orion capsule and that upper stage.
The MSA, I think, is a great example of a couple things. One, it's actually a piece of hardware that we're flying on an early test, but we're also going to fly for the long term. And so this is the same design that we'll use when Orion's on the SLS and we're actually flying people.
Today we've been taking the two unique pieces of hardware that are supposed to have a common interface, basically lowering them together, bolting and making sure that they fit.
Well, we're going to test a lot of the key systems on Orion and also for SLS with the upper stage of the MSA that are going to be used when we fly people into deep space.
Most recently, we've been involved with NASA with the SLS development, using our unique forming technology along with our other core processes in terms of machining, welding, heat treating, and inspection technologies. Really is a one-stop shop is what the way you would describe it.
Right behind me you have the first weld development cap, or I think you call it the weld confidence cap. The production order will start deliveries in 2014. Spacecraft also builds the domes for the upper stage Delta IV vehicle, which will be used for the EFT1 flight, as well as the first 2 production flights of the SLS program.
For the SLS PDR, our primary role was the overall communication and outreach support that we provide back to Todd May's office for SLS. We provide all of the communication support for that particular team, that program and project.
Well, it's a preliminary design review, and primarily it's a technical review to make sure that the design is acceptable and at the appropriate level of maturity.
There's a lot of discussions, there's a lot of meetings across the board, from technical, cost, schedule, performance data, safety, human factors.
It's like a health check on the program. Those of us that are working on the program, we've got our head down, we're doing our pieces. And sometimes when you're working real close to things, you don't necessarily see everything.
So there's so many moving parts and so many things going on at the agency, as well as the center, that to show people that we are moving in the right direction, to pull together the complete story of where we are as a program.
Watching at it from a higher level headquarters viewpoint, it's just gratifying to see the accomplishments that the teams have made and continue to make every day.
For CT2, we're doing modifications not only to make it last another 20 years, but also to uprate the load capacity. The main project we're working on right now is the roller replacement project, which is the roller assembly. It's actually the rollers, the shafts, the bearings that support the crawler. Actually, if you go there, you'll see trucks A and C jacked up and on cribbing. And that's the first time in the career of the crawler it's ever actually been jacked off the ground. So that the guys have easy access to the roller assemblies. And they're in the process now of removing the old rollers, old shafts and old parts. Once they've done the line boring, that's when they'll start assembling the new rollers and the new shafts and the new bearings and the new sleeves and new adapters and new plates. So there's quite a bit of work, and that work will go, well, from August through October. So there's going to be a lot of trucks delivering a lot of steel here at Kennedy.
We've started actually the new design for flame deflector, as well as refurbishment of the flame trench, and that's because of the new requirements for SLS and commercial vehicles. We've started the demolition of the flame deflector. We've got concerns of, due to age and the debonding of the flame trench structure, this would possibly be a safety hazard for our new program. And that's why we had to go in and do a new design and refurbish this flame deflector and flame trench.
These pieces here, they're not just one program, it's not just one mission, it's part of a capability that will enable this country to be a leader in space, to continue to take people from the Earth well beyond low Earth orbit out into deep space. And this is the hardware that will do that over multiple decades in the future.
So the work that's been accomplished so far is primarily structural type work, right? It's a lot of drilling, a lot of secondary structure installation, mechanical structures, the support structures. The next step is starting to install the subsystems. When we actually perform the welding on tubes for propulsion and the environmental controls and life support systems, those have to be at a higher level of cleanliness. When you look at the facility, there are these very large walls that are on the perimeter of the structure itself, and those are called HEPA filter walls. We can perform clean room work for the tubing concurrently while on the outside doing more standard clean room. So our goal is next summer sometime to turn the vehicle over, early summer, over to the ground operations organization so they can start their processing.
Well, the service module is attached below the crew module, and it has the prop tanks and the engine, radiators, solar panels. The service module all came in pieces. There's 49 composite panels on the SM. The actual structure itself is aluminum. That's the core skeleton where these composite panels were attached to. After the CM releases and the CM returns to Earth, the SM will just burn up with the upper stage of the Delta IV.
We performed two primary tests so far. The proof pressure test, which is just the pressure vessel, and that is That is put into the proof pressure cell. It's pressurized and a relatively high pressure. We're testing how well the vehicle was built. And then the follow-on test is the static loads test, where the vehicle goes through 8 different loads test cases. And so the vehicle is put under pressure, it's put under tension, it's put under compression. The whole intent is to simulate similar conditions that the vehicle would experience, say in flight, in launch, and also in landing and recovery.
We usually get the abort motor first, and for this mission the abort motor is inert, being a nominal flight.
We're going to have instrumentation on it to again understand more about the loads and environments that we expect to see in flight, but it will be an inert propellant that's cast into the motor.
This time we got the jettison motor next, and that's the only live component of this vehicle. We do a nominal jettison, the jettison motor fires, the last separates from the CM, and the CM continues on its mission.
You know, one of the challenges of any new system is understanding the loads as you ascend up through the atmosphere and the dynamics, the acoustics, and we'll be able to gather a lot of that information.
The back shell, it looks, though it looks the same as what we flew on shuttle, it is different. We kind of took the best aspects and put them together to meet Lockheed Martin's requirements for the Orion capsule. 2 major things we're trying to accomplish here. One of them is to prevent micrometeorite damage when we're on orbit for long duration. The other, of course, is the re-entry aspect. The skin that you see on the capsule, what you would see on orbit, sits on top of a composite substrate, what we call the back shell panel, that when combined together gives you the complete back shell. There's some sections that have some very complex geometry. So what we're going to do for the first time is take a substrate that's built by Lockheed Martin and put it together with the tiles that are manufactured by Jacobs and validate the fit up. Like any test vehicle, you're heavily instrumented. We're going to come back with a tremendous amount of data on how the system performed.
This first flight test of Orion is really to understand how the heat shield performs, and that heat shield's going final manufacturing at Textron.
Textron's had a long association with NASA and working in the space area for space protection.
The technology today has advanced tremendously. Our manufacturing technology has advanced, but ironically, we're still using a material that has proven itself for the last 40 years.
Avcoat is a very efficient ablator, and as an ablator, what it does, it allows us to protect the capsule from the high heating that occurs during re-entry.
There is no material, non-ablator material, that can handle that kind of heat. You have to shed away the heat. Basically what you're doing is you peel off the layers of the heat shield, you're taking heat with it.
When we apply Avcoat to the heat shield, we bond the honeycomb onto the carrier structure, and then we inject the Avcoat ablative material into the cells. The honeycomb acts as a crack arrestor and gives it rigidity and strength as a whole.
We know we're on the critical path for the Orion program, and so our employees are literally working all hours, all days of the week to make sure that we hit our schedule. We know there'll be more heat shields coming, and we're very excited about that. Our job is to make sure they're perfect.
The development programs I find just awesome, because this is where you're coming up with the new ideas, you're creating the new vehicles, you're pushing the boundaries in essence.
You can feel that we're going to go do this. The hardware is starting to come. The Orion hardware is getting ready for its first flight test down at the Kennedy Space Center.
The excitement is here. We are really ready to get going. So we are far from being out of space. We are really getting ready to go into space.
That's so rewarding to see our focus into what's next, because this really is our future.
I know the day that we fly this thing, there are going to be thousands of people that are going to be excited, that are working on this, and the NASA workforce and the contractor workforce. We're going to be proud of the work that this team has done, and I think we're going to be proud of our country too. It's going to be a pretty exciting time.
I'm ready to build a rocket, and we are ready, and we want to build it on time.
It was a busy third quarter for NASA's Exploration Systems Division. The first liquid hydrogen tank barrel segment for the core stage of America's new Deep Space Launch Vehicle was recently completed at the Vertical Weld Center at NASA's Michoud Assembly Facility in New Orleans. The segment is considered a confidence barrel segment because it validates that the Vertical Weld Center is working the way it should. When all segments are complete, the 212-foot core stage will be assembled in the Vertical Assembly Center, now under construction. In August, a 31-inch scale model of the SLS Core Stage B2 test stand was successfully tested in a wind tunnel. The actual B2 test stand, located at NASA's Stennis Space Center in Mississippi, was originally built to test Saturn rocket stages. The stand is being renovated to enable testing of the SLS core stage. The core stage with 4 RS-25 rocket engines will be installed on the B2 stand for propellant fill and drain testing and 2 hot fire tests in late 2016 and early 2017. In August, the largest 3D printed rocket engine component ever built by NASA, an injector, was tested during an engine firing that generated a record 20,000 pounds of thrust. 3D printed parts have the potential to drastically reduce the time and cost of producing future flight engine components. In September, the Orion stage adapter diaphragm arrived at the Marshall Space Flight Center to undergo pressurized testing before being integrated with the spacecraft's stage adapter, certifying it for flight conditions. The component is an integral part of the stage adapter that will connect Orion to a Delta IV Heavy rocket for NASA's Exploration Flight Test 1 in 2014. The diaphragm, a lightweight composite structure, serves as a barrier between the upper stage of the launch vehicle and the spacecraft, preventing hydrogen gas buildup from the rocket beneath the spacecraft before and during launch. At the Kennedy Space Center in Florida, one of the launch pads at Launch Complex 39 is undergoing extensive upgrades to support the agency's 21st century space launch objectives. A new universal flame deflector and trench will be completed in early 2015 and will support the new Space Launch System rocket and possibly a variety of commercial launch vehicles. For more than a year, NASA's Crawler Transporter, CT-2, has been undergoing a major tune-up in KSC's Vehicle Assembly Building. The crawler modifications are designed to enable the vehicle to transport heavier launch vehicles, including SLS, to the pad. Once the roller bearing work on half the crawler is completed, it will be prepared for a test rollout scheduled for January 2014. After traveling 3,600 miles above the Earth during the Exploration Flight Test 1 mission in September 2014, Orion will splash down in the Pacific Ocean, where it will be recovered with the help of the United States Navy. In August, with the Navy's USS Arlington stationed against its pier in Virginia, divers in small boats led the test capsule to the flooded well deck of the ship. With the capsule in position over the recovery cradle, the water drained until the capsule settled. Navy divers prepared for the recovery test in Norfolk by training in the 6.2 million-gallon pool at NASA's Neutral Buoyancy Lab near the Johnson Space Center in Houston. In July, the Orion team successfully conducted the Parachute Test Vehicle PTV-5 airdrop test at the U.S. Army's Yuma Proving Ground. 17 parachutes were deployed during this test. 9 were test technique related and 8 were the Orion system parachutes. At the Operations and Checkout Building High Bay at the Kennedy Space Center, the Orion team completed hundreds of welds and installations for the spacecraft's propulsion, life support, and environmental control systems. At the Johnson Space Center in Houston, NASA Administrator Charles Bolden welcomed 8 new astronaut candidates. This group will be among those who may carry out the first ever human missions to an asteroid and onto Mars. In October, recorded Orion telemetry was successfully transmitted between the Mission Control Center in Houston and the White Sands Communication Facility in New Mexico. White Sands will be used during the EFT-1 flight to receive and retransmit the Orion spacecraft telemetry. In late September, NASA astronauts Rick Linehan and Mike Foreman tried out a prototype display and control system inside an Orion spacecraft mock-up at Johnson Space Center during an Orion ascent simulation. Over the course of 2 weeks, 10 crews of 2 astronauts each performed launch and abort simulations inside the Orion mock-up to fine-tune the design of the displays and controls.
As 2013 wound to a close, NASA's Exploration Systems Development Division powered through an array of tests and milestones. Vehicle manufacturing, facility construction, and systems testing for NASA's all-new Space Launch System are progressing rapidly. Meanwhile, Orion and the Ground Systems Development and Operations programs prepare for the upcoming launch of Exploration Flight Test 1. The Orion Stage Adapter Diaphragm is a lightweight composite structure that protects the Orion crew capsule from hazardous gases produced by the upper stage engines. The diaphragm was recently pressure tested by joining it to the adapter and sealing with a vacuum. This pressure test simulated atmospheric conditions the hardware may experience during flight and is another essential milestone to ensure crew safety. The Space Launch System's Adaptive Augmenting Control System was tested at the Armstrong Flight Research Center in November. To test the system, SLS's automated avionics computer was installed on one of NASA's versatile FA-18 jets for analysis and validation. The Adaptive Augmenting Controller is an autonomous course correction program designed to instantly detect and adjust to unpredicted changes in flight. By exercising the system in an FA-18 research jet, engineers were able to run dozens of scenarios on each 90-minute flight. Successful deployment of this innovative control system will increase performance and robustness of the rocket as it is steered along the path to deep space. At Michoud Assembly Facility, the first propellant tank dome was completed on the circumferential dome weld tool. The massive propellant tanks used on the SLS core stage are unlike any that have ever been made before and require new tools and processes for construction. The nearby Vertical Assembly Center will house one of the world's largest friction stir welders, which will be used to assemble the liquid hydrogen and oxygen tanks. Last November, 90 trucks poured 900 cubic yards of concrete foundation in preparation for the new Vertical Assembly Center's tower structure and welding elements. This amount of concrete is similar to a foundation for a major modern hotel and will accommodate one of the largest welding tools in the world. With the launch of Exploration Flight Test 1 less than a year away, the Orion program is conducting more frequent, critical testing. In October at the Kennedy Space Center in Florida, the avionics system was installed in the crew module and powered up for the first time. The spacecraft came to life and performed as expected in a series of system tests. In December, NASA's Super Guppy arrived from New Hampshire, carrying Orion's most critical safety component, the ablative heat shield. The world's largest and most complex heat shield will protect future crews as the capsule plummets through the Earth's atmosphere, traveling more than 20,000 miles per hour. The heat shield will experience temperatures nearing 4,000 degrees Fahrenheit. Orion's service module was lifted for a test fit to the spacecraft adapter it will use on Exploration Flight Test 1. With the help of an air-bearing pallet, the adapter was positioned beneath the service module for alignment. A modified version of Orion's launch abort system was completed for the spacecraft's first mission. The launch abort system consists of 3 motors: the main abort motor, the attitude control motor, and the jettison motor. Because Exploration Flight Test 1 is an uncrewed launch, only the jettison motor of the abort system will be used to separate the structure from the crew module. Across the country in Sunnyvale, California, Lockheed Martin conducted secondary testing of the fairing panel separation from Orion's service module. These 14-foot-tall protective panels will be jettisoned after the craft reaches an altitude of 560,000 feet. Each panel has 6 breakable joints that fire apart, followed by 6 explosive separation bolts, sending them safely away from the capsule and service module. Lockheed Martin also successfully conducted the first of many forward bay cover jettison tests. After Orion completes a deep space mission and returns to Earth, it will jettison its forward bay cover at an altitude of 23,000 feet. The cover protects the crew during launch, flight, and re-entry, but must be jettisoned to allow Orion's main parachutes to deploy. At KSC's Vehicle Assembly Building, engineers test fit 4 ogive panels to the Orion ground test article. These 4 panels will cover the Orion capsule during launch and attach to the launch abort system. The ogive panel confidence fit was one of many tests designed to simulate the procedures for manufacture, assembly, and stacking. Although NASA and the U.S. Army may seem like unlikely collaborators, both agencies face the same challenges of keeping their men and women safe from chemicals and explosive projectiles. This mutual interest led to NASA's acquisition of 4 mine-resistant, ambush-protected trucks for use as emergency escape vehicles from Launch Complex 39. The 40,000-pound MRAPs came from Red River Depot in Texas and will be ready for use after some minor modifications. Launch Complex 39 is also getting an upgrade to its mobile launcher. The 405-foot steel tower is being reconfigured and strengthened to accommodate the weight, size, and thrust of the SLS vehicle. After a successful year of construction and testing in 2013, NASA's Exploration Systems Development Division looks forward to its biggest test yet, the flight of EFT-1 in the fall of 2014. ...2014 is off to an amazing start as NASA rockets towards this year's launch of Exploration Flight Test 1. The Orion program began the year with several major milestones. The service module was completely finished in January at Kennedy Space Center in Florida. The service module is the part of the spacecraft that contains all of the structural elements, spacecraft adapter, payload fairings, and crew module separation systems the EFT-1 capsule needs to conduct its high-altitude orbital testing. In February, the completed service module was stress-tested for the final time. The structural loads test proved that the vehicle will endure the physical stresses of its upcoming flight. After the test, the service module was ready to attach to the crew module. A test of the forward bay cover and parachute system was successfully passed in January at the Yuma Proving Ground in Arizona. After the Orion mock-up was dropped from a plane, the forward bay cover separated from the capsule, allowing the parachutes to release as the crew module descended safely to the desert floor. The capsule, parachutes, and forward bay cover were recovered and subjected to additional testing in the following months. In February, the Delta Mariner delivered 2 of the core and starboard boosters for the Delta IV Heavy rocket. After the boosters go through stringent testing and processing in the Horizontal Integration Facility, they will roll out to Launch Complex 37 for EFT-1's launch later this year. A full-scale mock-up of the Orion capsule was delivered to Langley Research Center in March. The mock-up will be used to perform a variety of static and impact tests to evaluate various water landing scenarios in a wide array of different conditions. At NASA's Kennedy Space Center in Florida, upgrades and modernization of the multi-payload processing facility continue as the building is readied for Orion processing support. By April of next year, the MPPF will have updated structural elements like environmental control systems, high bay doors, and emergency systems. The facility is also upgrading spacecraft preparation elements such as fuel and breathable gas systems, time-critical installation equipment, and ground support equipment storage. In January, the Crawler Transporter 2 completed a test drive on new traction roller bearings in 2 of its truck sections. The new roller bearings are one of several upgrades to the Crawler Transporter, which will carry the significantly heavier Space Launch System out to Launch Pad 39B. The other 2 truck sections of the Crawler Transporter will also receive new roller bearings and complete a follow-up test drive in November. In February, NASA and the Navy tested procedures to be used during Orion recovery operations. After launch and re-entry simulations, the forward bay cover and parachutes were successfully retrieved from rough waters off the California coast. The ocean turbulence in the well deck of the recovery ship made it difficult to secure the Orion test article. The challenges experienced during this test reinforced the necessity of practicing spacecraft recovery. The circumferential dome weld tool produced a second liquid oxygen tank confidence article at the Michoud Assembly Facility. The confidence tank verified that the weld tool is capable of producing the core stage tank up to the exacting standards the Space Launch System will require. A composite cryotank for liquid hydrogen was also produced and delivered to Marshall Space Flight Center aboard NASA's Super Guppy cargo plane in March. The advanced composite cryotank, which could benefit many of NASA's deep space exploration spacecraft, will undergo a series of structural pressure tests later this year. A scale model of the SLS was used in acoustic testing to see what effects high and low frequency sound waves will have during launch. The model's core stage fired for 5 seconds while an array of microphones collected the acoustic data. A full assembly test with the scale rocket motors will be conducted later this year. In March, NASA Administrator Charles Bolden visited Marshall after the software integration team powered up the flight avionics, which includes hardware, software, and operating systems for Space Launch System. Known as First Light, the flight computers of the SLS simulated the flight path the vehicle will experience during launch. NASA's Exploration Systems Development Division is flying through production, testing, and launch, as 2014 promises to be one of the most productive and exciting years in recent space history. Halfway through one of the most productive years in recent space history, NASA's Exploration Systems Development Division is moving humans ever closer to deep space exploration. The Space Launch System, NASA's next-generation deep space launch vehicle, had an intense spring full of development and testing. Testing on the avionics system, responsible for controlling the Space Launch System's solid rocket boosters, began in April. The avionics system will ignite, steer, and jettison the two solid rocket boosters, and will continue to undergo an extensive series of tests this summer. In May, structural tests on the SLS booster forward skirt proved it could withstand millions of pounds of launch stress during a series of ground tests. The SLS core stage will be powered by 4 RS-25 engines that are now undergoing preparation for test firing at the Stennis Space Center in Mississippi. Following initial testing, the engines will be integrated with the core stage, and the entire assembly will be tested on the B-2 test stand. Because the SLS core stage is 50% longer than the Saturn moon rocket stages, the mothballed B-2 test stand and the main derrick crane are currently being modified and upgraded to accommodate this enormous structural element and powerful main engines. Production on the core stage structure and propellant tanks continues at the Michoud Assembly Facility in Louisiana. 34 primary structure components and 20 rings have been welded to build the core stage propellant tanks, including 9 barrels and all the rings needed for SLS's first flight. A 5% scale model of the SLS was ignited to test how both low and high frequency sound waves will affect the rocket as it fires its solid rocket boosters and main engines on the launch pad prior to liftoff. These ongoing tests are collecting data from over 200 sensors to study the acoustic impact on the spacecraft and verify the design of its water-based sound suppression system. A major milestone in the effort to transform Kennedy Space Center into a multi-user spaceport was met when Ground Systems Development and Operations completed the initial design and technology phase of the preliminary design review. GSDO is modifying the spaceport's infrastructure to support several different spacecraft and rocket launch needs. Firing Room 4 at the Launch Control Center at Kennedy Space Center in Florida is being renovated into 4 separate launch areas to serve NASA and commercial users' needs. Designed to accommodate a multi-user spaceport, the new adaptable rooms can open up to give more space as needed by a customer's launch room parameters. Upgrades to the mobile launcher at Launch Complex 39 are underway, with significant progress toward advanced usability. GSDO is systematically modernizing the launcher to meet the increased needs of the more substantial Space Launch System. Upgrades include structural work, an improved sound suppression water system, a redesigned exhaust opening, new data connectivity to the Launch Control Center, and updates to the power, air condition, and fire alarm systems. After the Exploration Flight Test 1 mission is complete and the capsule lands in the Pacific Ocean, the Ground Systems Development and Operations and Orion programs and the U.S. Navy will retrieve the capsule and ship it back to Florida for reuse. The return process requires a series of pre-transportation operations, which were successfully tested in May. Workers practiced assembling a transportation fixture that will be used to move future Orion crew modules across the country. The newly renovated Flight Control Room at the Johnson Space Center in Houston played host to members of the media and top NASA officials in April. The White Flight Control Room will support the Orion spacecraft during NASA's deep space exploration missions. In May, the room was used in a joint integration simulation, along with a team at the Kennedy Space Center in Florida. The two teams simulated the pre-launch and in-orbit phases of Orion's mission and solved real-time problems, acting as the eyes and ears of the uncrewed spacecraft. The rigorous testing on Orion's parachute system continued in April and June, proving the parachutes are capable of surviving potential failures during both re-entry and launch abort scenarios. The first test simulated an abort scenario by dropping the capsule from a height of 13,000 feet and releasing the main parachutes before the drogue parachute could deploy or the vehicle could straighten itself out. The second test pulled the capsule from the C-17 airplane at an altitude of 35,000 feet, with one of the main parachutes intentionally rigged to skip a crucial phase in the unfurling process. Both tests demonstrated the parachute system can tolerate unexpected failures and still carry the capsule safely to the ground. After 2 years of intense production and testing, Orion's massive heat shield was successfully attached to the crew module in Kennedy Space Center's Operations and Checkout facility. The 16.5-foot wide ablative shield will protect the capsule from re-entry temperatures of up to 4,000 degrees Fahrenheit. A center of gravity test confirmed that all of the ballast was properly installed in the crew module. The test validated the Orion team's computer models used to calculate the amount and location of ballast needed to properly balance the crew module. With the heat shield securely attached to the capsule, the crew module was then stacked on top of the service module in June. The stacked modules will undergo electrical, avionic, and radio frequency tests to prepare for the Exploration Flight Test 1 in December. In May, astronauts at the Neutral Buoyancy Laboratory in Houston trained underwater in newly modified spacesuits to work through simulated operations for NASA's asteroid retrieval mission. A month later, a naval team worked with Orion recovery specialists to train for a set of procedures to safely retrieve the capsule and forward bay cover. As Exploration Systems development closes in on December's launch of Exploration Flight Test 1, NASA centers nationwide stride toward the Moon, Mars, and beyond.
Prop go. Vital. Go. Guidance. Go. LSO. Go. Weather. Go. Pointing. Pointing scope. CDH. Go. GNC. Go. Ecom. Go. Inco. Go. NGC. Go. Engine start box. Go. Prop report range status.
Range green.
Upper stage LH2 secure at flight level. Status check. Go Delta. Orion.
5, 4, 3, 2, 1.
And liftoff at dawn. The dawn of Orion and a new era of American space exploration. Flight Fido. Go Fido. Yes, sir. Just passed through Apogee. The altitude was 3,132 nautical miles.
RS-25 rocket engine.
systems development and operation.
guess you're about the only person around that doesn't have TV coverage of the scene.
That's all right, I don't mind a bit.
Okay, you got the flag up now, and you can see the stars and stripes on the lunar.
Are you getting a TV picture now, Houston?
Neil, yes, we are getting a TV picture. You're in our field of view now.
That's one.